Welcome everybody to Interface Fluidics' webinar on the gaps in traditional fluid testing technologies and how high pressure, high temperature fluid analysis can help improve decision making. My name is Stuart Conor. I'm the CEO and co-founder of Interface Fluidics, and I look forward to presenting this material. As I said before, if you have any questions or comments throughout the material, please feel free to drop your questions or comments in the chat or in the Q&A section. With that, I will head it off here. So today the agenda is we'll run through an overview of the technology, highlight the gaps in traditional fluid testing that we see, how high pressure, high temperature fluid testing can now fit into many new workflows, and how things have changed over the last few years. Talking a bit about some of the impact that third-party advisors can have on the traditional fluid workflow, whether that is from an engineering perspective at a oil and gas company, or how we can help folks that provide chemistry to the industry. A few different perspectives we have on how to mitigate risk effectively and workflows. And then finally, understanding how we can, the impact that proper data verification can have on results. So today's all about addressing the hidden gaps. So our job at Interface, the way we see things, is to uncover the often overlooked gaps in traditional fluid testing and helping folks recognize how those overlooked gaps actually reduce well performance. And this is very close to our hearts at Interface, because that's why we originally started the company. When we started the company, myself and my co-founder Tom were both working at upstream E&Ps and really struggling to get good data in a reasonable amount of time. And so we've really started to solve our own problem here at Interface. And I wanted to just talk a bit about that. So when it comes to fluid testing in the oil and gas industry, it's really all about the trade-offs that are required in traditional fluid testing. If you want to have a representative test, that means high pressure, high temperature, real rock, you're typically talking about either being able to do that, or if you're talking about bottle testing, you're really not able to get to the representative conditions. Many tests that are out there, you can either have a very qualitative test or a very quantitative test, and generally there's not a lot in between. Repeatability is often not possible with traditional testing, meaning you don't understand the precision of the measurement itself. You can look at fast and cheap or expensive and slow, and generally there's not much. There traditionally hasn't been much in between. And finally, we're looking at getting a single data point per measurement with traditional testing, or if you go with bottle testing, benchtop testing, you might be able to get a lot of data, but you're making a lot of these trade-offs of being representative, qualitative, and not very repeatable. And so Interface and Microfluidics, today is about where can we address these the things in the middle here? How can we get as much of the best of both worlds? And so just to build on that a bit, the typical tests that are done on a daily basis with most E&Ps upstream, we're starting with water and chemistry analysis. So what's in our water? So these are samples that are coming from the wellhead, and we're doing, looking at the composition of water, the composition of oils and gases, and looking at how things mix at the benchtop, in things like test tubes. We use bottle testing, where we'll take, for example, if we're looking at compatibility, we'll take a formation fluid and an injection fluid and mix them together in a bottle. Maybe that bottle is heated, and look for things like emulsification or visual evidence of precipitation, for example. And then finally, core flooding and sort of other core flow tests are sort of the gold standard, where you get you're able to get high pressure, high temperature, use the real rock if you've got the money and the time for it. It's a very good test, but like I said, it can often be slow, and it can often be difficult to repeat. And so, the core thing that goes across all of these is you can sort of have one or the other, typically not both. And ultimately, high pressure, high temperature is the thing that people are trying to get as close to as possible, and it has shown over time to be very, very important. But these measurements often will take too long to be useful operationally. They're great for learning, but they're not great for making decisions on the fly. Often people will think that this is going to cost me hundreds of thousands of dollars in months or years in order to do a really great large scale study. And finally, like, you can't actually get repeatable results. You're never going to see a result graph of recovery factor from a core flood that has multiple runs on it. It's just not possible. And so we don't know the repeatability of the data. Or if we do know it, it's not very good. And so there is this gap of what can we do in the beaker scale, where we have fast, cheap capabilities. We can use our eyes and see what's going on. We have the ability to make judgment calls and sort of look at this qualitative characteristics of what's happening inside the beaker. They are very quick. And typically, this is not going to cost you a lot of money. When we're looking at core scale testing, high pressure, high temperature, traditional methods, we are able to get the temperatures, the pressures that we're looking for. We are able to get fluids flowing through rock and confined systems, having that reactivity in the system. We also have the judgments of the people that are running these experiments. They're very good at it. They have a lot of expertise, but they do take a lot of time, typically weeks, or if you're looking at doing very low permeability core flooding, months, and the cost associated with that. So this is the gap that I'm talking about today. So how can we make high pressure, high temperature fluid analysis actually accessible? We believe that HPHT testing should be an essential part of your assets workflow, driving the business forward, because if we can make it accessible, we can start giving people the data they need, a new kind of data, a new way of thinking, which allows us to tackle problems we previously thought were uneconomical or impossible to solve. So at Interface, we created a test that is sort of the goal to be sitting in between and bridging that gap between beaker scale testing and core scale testing. And we've become the world leaders in fast, visual, repeatable fluid analysis at the pore scale. So microfluidics is the technology that we use on a daily basis. I see a question came in here. Let me just pop that up here. Downhole fluid analysis on wireline. I'll get to that at the very end here. So thank you for the question, and I'll come back to that. So microfluidics is the technology that we use at Interface that allows us to sort of bridge this gap. And it's the study of fluid flow at the micrometer or nanometer scale. You can see here it was first developed back in the 1950s and 60s for things like water flooding and understanding what's going on inside of water floods. But that technology was then sort of co-opted over into the biomedical space, where it was developed significantly into basically to a society-changing technology. Our world looks different because of microfluidics in the biomedical space. And at Interface, we're taking this technology that was originally developed for the oil and gas space and bringing it back to oil and gas, and utilizing all the advancements that have been made in the 70 years since then, and providing this high level of HPHT testing. It allows us to take sample sizes down from liters or hundreds of milliliters at the least, down to a single milliliter in some cases. We use a tech, and microfluidics allows you to do amazing things like create reservoir analogs. So this allows us to recreate the permeabilities, the porosities, the pore throat size distributions that are seen in the real rock and the real core that we use, recreate that for our clients, and then run experiments actually flowing fluids through these synthetic porous media, and getting you the repeatability that is lost in traditional porous media, while maintaining the things like grain size distribution and actual permeability and porosities. So this leads us to what we call sort of the next generation of fluid analysis. So we use the characteristics of your reservoir, the temperatures, the pressures, real reservoir, porosity, permeability, as well as your fluids. So real oil, live oil, dead oil, whatever you got, real chemistry, real water. It's important to use these real fluids so that we understand how they interact. And then we use microscopes and cameras to actually visually observe how these fluids behave, look at the displacement and how they behave inside the porous media and if there's any issues. So like I said before, we use visual analysis. So you can see here on top of our hardware that you can see a picture of, this is our microscope camera. And it allows us to see in many different kinds of light, many different kinds of imaging technologies. So the first is fluorescence, which is really great at letting us see where oil is and is not. Bright field imaging allows us to see damage that's caused during production or injection processes, things like asphaltene precipitation, scale, wax, all of that kind of thing. And then finally, cross-polar microscopy, which allows us to understand how crystalline materials like waxes, for example, form and how they deposit into the porous media and if they cause damage and how that damage can be remediated. Now, this is not just a system that's all about flow through porous media. It's also fundamental fluid properties like PVT analysis, but we'll focus mostly today on the kinds of porous media applications that we have. You can see in the bottom left here, that's a graph of one of our results from one of our flowback tests. And this is a test that we're looking at evaluating how different injection fluids or different fracturing fluids impact production. And so you can see bigger numbers are better, but one thing you'll see on here is error bars. The interface provides the ability to actually rerun on the same porous media over and over again. So you get repeatability data. So you can see how sensitive is my system to the chemistry that I'm injecting. This is something you can't get any other place, any other way. So the workflow that we suggest to our clients is really not to eliminate anything that they're doing. We would never say, don't do what you're already doing. The bottle testing in the field, that gives you a good idea of what's going on in the moment, allows you to make quick, fast decisions. But microfluidics is a great next step because bottle testing often doesn't incorporate sort of the control that you'd find in a lab setting. And then if you move on to the core, microfluidics is really great at understanding fluid compatibility. How do different fluids interact at temperatures and pressures? But what it doesn't include is the actual real core material. Using real rock means that we're getting the reactivity of the system incorporated. So every one of these types of testing has a role to play, incorporates really interesting and important data. But this microfluidic capability really bridges the gap between the two to make high pressure, high temperature much faster and more economical than it traditionally would have been. You can run about 10 times the amount of data through a microfluidic system, or even 100 times in some cases, as you would a core for the same price. Ryan, just as a really quick answer, do we incorporate formation mineralogy? That's a complicated question, but in general, sort of sometimes. And I'll get into the detailed answer to that at the end here. And so, like I said, we've built this microfluidic system in order to bridge the gap between core testing and beaker scale testing. And so often, one of the things that you can think about when it comes to understanding fluid challenges and problems is, how many problems do you see on a day-to-day basis? Our job as external advisors is to build bridges, and overcome cross-disciplinary challenges. The industry is changing very quickly. Expectations on engineering teams are getting higher, and well performance and needs to be more predictable than ever. And when it doesn't happen, the question is why? So most operators that we talk to don't know that it's possible to manage their fluids better with just a little bit of work. And the best part is, at Interface, we've seen a lot of the problems, and I'll show you sort of an example of that in a minute, but it's not a meaningfully larger amount of work to manage your fluids better because we have these tools. Majority of the problems that people run into that result in lower well productivity or surprising well productivity can be solved and understood with just, typically we advise taking a proactive approach versus a reactive approach. So it's easier to say, well, what problems can I anticipate and deal with, rather than I had a problem, can I figure out why? I think everybody would prefer to be in the first state rather than the second. Hasnian, thanks for the question. You can do testing on the whole fluid system or systematically to understand different components throughout. And again, I'll try and get to a more detailed answer on that in just a few minutes here. So at Interface, over the last few years, this is sort of a menu of problems that we've worked on. And I said before that, third-party advisors have a role to play in that we see a lot of problems, and probably more problems and a more diverse set of problems than any one individual in any one asset, because not all assets have all the same problems. And so being able to have a 30,000 view of here are the different kinds of fluid problems that you can experience, and here are the other ways that other folks have dealt with those problems, looked for solutions, and potentially found them, means that we've got a different view, not a better or worse view, just a different view on these kinds of problems than your average engineer. So what we always say to folks is, when you should come to us. The first is early and often, mostly because, again, we can, we're not going to ask to get paid to give you a bit of advice on what samples to collect or when to look for problems and things like that. But some key triggers that you might consider bringing in an outside third party is if you're going to change your chemistry or change your water source. Anytime you have fluids that are a material part of what you're injecting changing, whether that's composition, sourcing, for whatever reason, this is an area, probably the #1 area where we help folks solve problems that have come up. If you see a change in production, or if you see wells that are not on that type curve, one of the things is we've spent so much time and effort getting really great at optimizing completions processes. For example, we've optimized the hardware and the frac process and our modeling to within an inch of their life, because that's how we gain the biggest advantages. But what we haven't done over the years is look really hard at fluids. For the most part, again, there's a lot of people that spend a lot of time thinking about fluids, but this is an area where it's hard, where often it's been hard to justify spending a lot of time. And I talk to a lot of engineers who they just know, they might not know, have really hard evidence that there's an issue or that there's a problem, but they just know that there's something they want to optimize, and they might not have a way to prove it. Trusting our guts is something that we do a lot in this industry. And this is something that Interface really specializes in, helping people understand, my gut is telling me something, can we look into it? So I just wanted to share a quick operator story about sort of where Interface can really come in and help understand what's going on. Because last year we worked with an operator in the Bakken who came to us looking for surfactant screening. They wanted to increase the amount of oil that's being produced out of their wells, and other folks in the area were trying surfactants to pretty good success. And so they came to us and said, let's look at how we can implement this technology in our operations. And so the first question we always ask is, what testing have you done? And so this is what they had done already. So we asked, is your water compatible? Because if you put a lot of money and time into spending on expensive chemistry like surfactant into an incompatible water system, you're wasting money. And so when you do traditional sort of bottle testing with their formation water and the water that they were going to use to frac, you can see looks generally good, no issues. But this is done at atmospheric conditions and room temperature. So Interface went on and said, okay, great, let's take a look at your fluids. Let's try and implement these surfactants. On the first test, the first time we tried to put that water that's now been combined onto a high pressure, high temperature system. We had a massive salt deposition and scaling happen. We were never even able to get this fluid that looks innocuous on the benchtop into the porous media at high pressure and high temperature. So the reactions change and the kinetics of those reactions change when you change the conditions that they're being done at. And so if you're not testing at reservoir temperature and pressure, you're missing the whole picture. So this project went very quickly from a surfactant screening project to a water screening project. And, we helped them identify water sources, and we helped them identify the problematic components of that water that they needed to either eliminate or find a different water source so that they could prevent this issue from happening again in the future. So I mentioned at the beginning, we're here to help mitigate risk at Interface. The way that we approach this and what we recommend to our clients is that the first thing we need to do together is understand the processes, the goals, and the challenges that are in play that we're trying to work on. Interface doesn't come in with a standard workflow. We don't come in and say, this is how you optimize your fluids, because what we've seen is that everybody's operation, everybody's challenges, and everybody's wells are all significantly different, materially different. And so we spend a lot of time upfront understanding your rock, your process, what are your water sources, what's in those water sources, who are your chemistry vendors, all of that in context with what are you trying to achieve? Why did you call us in the first place? Are you having issues? Do you want to prevent issues? If we can do that, I would say it's very common for us to send our clients off to somebody else because the problems or their goals don't align with what we can deliver. And so we like to help people find the right methods to solve their problems. That's our number one goal, even if it means that Interface isn't the one helping do that. The second is, if we determine that yes, Interface can help solve this problem, we're going to recreate that process and problem using our testing in our facility. By recreating the problem, we show folks that we can, many times people want to see, well, can we recreate this in the lab to understand it and control for those problems? We do that using obviously the visualization and analysis that comes from Sapphire Lab, whether that's a water flood, a polymer flood, a fractured reservoir, any application where we have two fluids coming into contact in the subsurface, we can help there. And then finally, the last piece is really getting down to solving for whatever the problem is. It's really challenging to control every variable in traditional testing, and that's a place where Microfluidics has a role to play, because we can do testing so fast and with such control that now we can actually start eliminating problems and narrowing down, well, what's the source of the problem that I'm dealing with? And that's not something that is easy to get to any other way. So through that whole process, the goal is, what's your problem? Can we solve it? If we think we can solve it, we'll run some testing. And then finally is, what's the least amount of testing that Interface can do to get you to X? The goal isn't to test every possible variable every time. That's not practical from an operational perspective, and it's not practical from a cash and time perspective. And so at Interface, we're always looking at what's the least amount of testing I can do to get the best quality of answer. And finally, I mentioned it before, but sometimes you just have a gut feeling of, what if I changed something? What if I did something else? There's a lot of people in the industry whose job it is to think about, what if we changed something? What if we did something differently? How can we improve? What are the stories or narratives that are driving that what if that need more depth, that need backup to actually either rule them out or move ahead with improving a process? Tom DeHaas, who's the guy in the background there, he's our chief technology officer and my co-founder. He was at Suncor before we started the company, and his job every year was take one of the thousands of technologies from our technology portal at Suncor and pilot test one, right? Go from thousands to one effectively. How do we do that? How do we collect enough data? How do we test hypotheses quickly and keep the risk low? That's the kind of thing that Interface exists to help with. And finally, really at the end of the day, we're all in pursuit of really delivering on clear objectives. So how can interface partner with you to collaborate with asset teams to achieve their goals? How can we help strategize by utilizing the right tools to define clear objectives and isolate the critical variables that are at play? And finally, can we add clarity? How do we minimize the amount of ambiguity in the data? How do we get to a clear forward path? And so finally, just to wrapping up here, what could be different if we didn't have the restrictions that are in play? If time and cost and repeatability were not the challenges that they are, what would you do differently? Because if we can help solve that problem, if we can solve for, well, let's make it faster, let's make it less expensive, and let's make it more repeatable. You start again, what questions would you ask that you can't get answers to today? And so with that, I'll turn it over to the folks at the questions here and see if there's any. I'll get into the more detailed answers here. So I'll address these in the order that they came in here. So where does DFA or downhole fluid analysis on wireline fit into the gap? I think downhole fluid analysis is a really great screening tool. It's really, I think, the gold standard for especially PVT analysis and reservoir characterization early on. It's not something that Interface performs, but downhole fluid analysis is very expensive. And, as accurate as it is not the same as using a laboratory grade PVT cell to characterize your fluids and characterize your reservoir. And so I think it is a good tool for using in early phase. But at Interface, what we're trying to do is deliver a tool that, for example, if you're doing wireline, you can bring Sapphire Lab that you see there, you can bring it to site, have your PVT done on site, and so that you have your sort of lab grade PVT analysis done in as close to real time as possible. So there's a role to play, and I don't think it's a great tool. I'm not sure if that answers your question or not. Let me know, post in the chat. Second here from Ryan. Do you incorporate the formation mineralogy into the creation of these flow cells? So the way that we think about it is, formation mineralogy, we're not using real rocks. So the goal here is at Interface is let's understand fluid-fluid interactions primarily. But that being said, our system has a silicon dioxide surface. And so from a compositional perspective, it is very, very similar, if not identical, to what you get in sandstones. And then as you get into more reactive components of the mineralogy, whether that's clay or more reactive rock, that's where the case of, well, we're not actually able to replicate the reactivity of the system, but we are able to replicate wettability and flow parameters so that we can understand how different fluids interact inside there. So to sort of put a bow on it, Interface is great at helping folks understand fluid-fluid interactions. That's the #1 goal typically. And then fluid rock, I would say generally you should use a rock. That's why we say there is a role to play for all of these tools. Third question here from Hasnian. Is the microfluidic testing done for the fluid system as a whole, or can it be used for specific components of the system individually? I think this is the strength of microfluidics. We can test each individual component as well as the whole together to understand the impact that each component in the fluid has on performance. So for example, if we're looking at a frac fluid and trying to understand, is this frac fluid going to be a high performing system or not in this particular well? What we're going to do is take the real oil from the system or the real reservoir water from the system, and then we'll use a control. So our control, we provide a control in all of our cases, and generally that is tap water. So just clean tap water, nothing in it, no chemistry, as the baseline for the porous media experiment. And then we'll build on that with, maybe we'll use the whole fluid system that you fracked your last well with. Real chemistry, we'll mix it on site. Breakers, scale inhibitors, biocides, all of that. The next, so that I would say you can test all of these things and understand the impact that they all have. Thanks, Ray, for your question. I'll answer that in just a second here. So from Bassi, how do you navigate the difficulties of collecting, transporting, and storing subsea samples of live oils and gas condensates for flow assurance studies? It's a real challenge. Typically, we partner with the experts in that field. We're experts at laboratory testing and laboratory technology, so we typically work with the traditional samples and sampling technology that would be done by a Schlumberger, Halliburton, other service companies like that. We do give advice on, volumes and which samples to take and when and what we think is going to have the biggest impact, but we don't get involved in actually doing the sampling and transportation. It's a major problem for a lot of our clients, and so that's why I said before, Interface's Sapphire Lab tool that's on the screen here is all about how can we take our hardware and bring it to the sample rather than bringing the sample to the hardware, because transportation of these fluids is very challenging, expensive, slow, can take months or years to get samples out of some countries into other countries. So if we could take this tool, bring it to them, then we can solve that logistical problem. Ray, can energized fluids be tested, CO2, nitrogen? Absolutely. Yeah, we do testing on live fluids. We do testing on pressurized systems all the time. CO2 is sort of a bread and butter for us, whether that's straight CO2 or CO2 foams and other chemistries like that. Yeah, absolutely. So a follow-up question here from Bassi. Have you been able to use microfluidics to combat the polymer degradation, increased OPEX, and complex emulsion problems associated with chemical enhanced oil recovery, ASP flooding with hydrolyzed polymers? So we've been able to, we do a lot of testing of chemical enhanced oil recovery. The system is, I'm not sure if we've been able to specifically answer that question about polymer degradation and increased OPEX. The way we approach these problems is, especially in the context of chemical enhanced oil recovery, is how can we get the system to be as representative as possible, number one. So we take extra time and care to make sure we get really great porous media and representations done in chemical enhanced oil recovery projects. And then, it's really all about your experimental method. Can we introduce the right shear rates, the right flow rates, the right viscosities, temperatures, pressures, all of that, getting the actual subsurface flow system. And then what we're looking at is displacement. Displacement is the number one goal, the name of the game, and looking at pressure drops. And so I think, to answer your question, I believe Interface can be a great tool in answering that specific problem. I don't think we've ever looked at specifically polymer degradation, but looking at emulsion characteristics and fluid compatibility, I mean, this is exactly why we created this system. I hope that answered your question. Let me know if I didn't, or if you'd like more detail. Can we create microfractures on the slides? Yeah, actually we do. So when we're fracturing, when we're testing hydraulic fracturing fluids, the porous media system that we create is actually a dual porosity, dual permeability system. So we're actually going to recreate the proppant pack as well as the matrix permeability and porosity. So we're going to have a high permeable zone. We also have a very low permeability zone that is down to in the orders of nanodarcies. And so you get this gating effect on the matrix where the damage actually happens. You can see damage happening in the proppant pack. You can also see damage happening in the porous, in the matrix, and both visually and in the results. So hopefully I've answered your question there, Stan. Bassi, I'd encourage you, send me an email. I'll just type it in the chat here. And you can, well, that wasn't to everybody. Let me, Conor, if you can link my email address in the chat for everybody, that'd be great. Do you manufacture the microfluidic chips on demand? They are glass made. What are the pressure limits? So I'll take those in order. Yes, we manufacture the chips on demand because in order to run a good experiment on these chips, you have to design a system that is representative. Interface Fluidics is the only fully vertically integrated microfluidics company on the planet. So we do everything from design, fabrication, quality assurance, running the experiments, working with our clients to understand their problem, and actually delivering the data. That means that we design custom analogs for all of our projects for all of our clients, and that's just the expectation. We don't think you can run a really great experiment without building something that is truly representative. And the reason we can do that is because of that vertical integration. It doesn't add material cost to actually doing business for Interface or for our clients. They're glass, they're actually they're silicon wafers that are etched to have the porous media pattern, and then we bond glass, borosilicate glass on top. So I think that answers the question. What are the pressure and temperature limits? 15,000 psi and 400 degrees Fahrenheit. In metric, that's 1,000 bar and 200 degrees Celsius. One more question here from Bassi. How long between collection time at field to arrival time at the lab do you consider as a maximum for HPHT multi-phase fluids? That really depends on what we're making the measurement of. So if you want to make a measurement of emulsions, for example, you need that time to be as low as possible. And there's a lot of ways you can manage that. When it comes to things like dead oil samples, there's really not a huge rush. When we're doing single phase pressurized samples, Interface has all the capabilities to recombine and make those samples single phase and representative again. So it really depends on the specific need of the problem there, Bassi, but it's something we integrate into our operational planning process. For live oils, I think it's we have all the ability to recondition fluid samples, so it's generally not a problem as long as they've had good chain of custody before they reach us, I would say. Wax deposition tests. So I would say, the important thing for when we do wax testing for our clients is, again, something that's that temperature sensitive. The way we would prepare a sample is making sure we get, often for example, wax, you may have a compromised sample coming out of the wellhead. And so it's really challenging. If you have fluids that are sort of actively depositing waxes and want to understand the characteristics there, the way we would do that is get the wellhead sample, get it really hot, make sure everything goes back into solution, and then look at through a control, using a controlled temperature drop process, you'd be able to actually measure wax appearance temperature, how different chemistries impact that wax appearance temperature, the characteristics of the actual crystals as they come out of solution. So I don't want to simplify it, but I think wax deposition is something we do often and can look at, and typically like to design the sampling process around the actual problem that we're solving. Great. All right, last call for questions. Thank you very much, everybody. I appreciate your time and attention today. If there's any other questions, Conor posted my hot question coming in off the bat here. Is it possible to create a specific mineral on the surface of a microfluidic device to prepare for the real situation? It is possible. You can deposit these minerals into the system and look at how they react. What we typically tell people is you can do that. It's going to add significant cost. And one of the benefits of microfluidics is the repeatability. Anytime you start now depositing solids into these chips, you start impacting the repeatability of these experiments. And so if the question is, are these fluids going to have problems in the presence of the real mineralogy? Often what we'll tell people is you're better off to use a real rock and use a real core flood, for example, to measure those fluids. The trick, though, is make sure your fluids are compatible, or at least high performing, before you put them into the core system. Because if they fail in the core, but they were successful in the microfluidic system, we know that the rock fluid compatibility is the source of your problem, and you can start going down that investigation. If you go straight to the core and it fails, and you haven't verified that the fluids are compatible previously, then you're not going to end up with the certainty that you would have this way, because you don't know, is it the rock problem, or is it the fluids? Hopefully that answers your question, Ali. Let me know if you'd like a follow-up. You use from Bassi again. You use cross-polar microscopy for wax appearance tests. Are they accurate for opaque oils? Absolutely. These oils are, when we're putting them into the microfluidic channels, they're actually just a few tens of microns deep. And so there is some in some cases when we're using fluorescence microscopy, you typically only are going to see the first few microns of the oil in the reflected mode. But since we're using cross-polar and bright field light, oils that are opaque are not entirely opaque, and we're able to actually see those wax crystals. So we have not had a problem there. I'm not saying we would never have issues with the opaqueness of oils, but that has not been a problem in the past. We've done everything. We've been able to work all the way through bitumen with good success. So I don't believe there's going to be any issues there. Question here from Landra Lopez. Do you think adsorption plays a role when dealing with polymer surfactants? I believe that's the primary method that these products interact with. In the case of formation damage or skin damage or wettability alteration, I think adsorption is the primary mode that we see these chemistries interacting with porous media. So, often we'll see in a polymer system, you can actually measure the effective permeability and effective porous media characteristics pre and post injection with polymers by looking at pressure drops and flow rates. So I would say yes. Surfactants, obviously they're going to be interacting with both the two liquid phases, but they also modify wettability in our systems. So you can actually measure and control wettability in a microfluidic device very, very accurately. And then you can also report on how the polymers or the surfactants specifically change wettability inside of our systems over time. So I hope that answered your question, Landra. Let me know if you haven't, or again, I'd encourage everybody to send me an email or give me a phone call or a text message. Thanks, everybody.